Welcome to this comprehensive guide on ensemble learning in machine learning. This is AI Academy, and in the next 15 minutes, we'll explore one of the most powerful techniques in machine learning that can significantly boost your model's performance. By the end of this video, you'll understand what ensemble learning is, why it works so well, and how to apply different ensemble methods to solve real-world problems. Here's what we'll cover in this video. First, we'll start with the fundamentals, what ensemble learning actually is and why it's so effective. Then, we'll dive into the three main types of ensemble methods, bagging, boosting, and stacking. We'll explore popular algorithms like random forest, XGBoost, and voting classifiers. Finally, we'll discuss when and how to use ensemble methods in your projects, along with their advantages and limitations. Let's start with the fundamental question. Why do we need ensemble learning? Imagine you're trying to predict house prices using just one decision tree. This single model might work well on your training data, but it's likely to overfit and make poor predictions on new data. Single models, no matter how sophisticated, have inherent limitations. They can be biased, prone to overfitting, or simply not complex enough to capture all patterns in your data. This is where the wisdom of crowds principle comes in. Just like how asking multiple experts for their opinion often gives you a better answer than relying on just one expert, ensemble learning combines predictions from multiple models to create a stronger, more robust prediction. It's based on the simple yet powerful idea that the collective intelligence of multiple models is often better than any individual model. Ensemble learning is a machine learning technique that combines multiple models called base learners or weak learners to create a single, more powerful predictive model. Instead of relying on one model's prediction, we train several models and then combine their outputs through various methods, like voting, averaging, or more sophisticated techniques. The key insight is that while individual models might make errors, these errors often cancel out when we combine multiple diverse models. Ensemble learning works because of three key principles. First, it reduces variance. If individual models overfit in different ways, averaging their predictions smooths out these inconsistencies. Second, it can reduce bias by combining models that might be biased in different directions. Third, it improves robustness. If one model fails on certain types of data, other models in the ensemble can compensate. This leads to better generalization and more stable predictions across different data sets. Ensemble learning has three main categories of methods, each with its own approach to combining models. Bagging focuses on reducing variance by training multiple models on different subsets of data. Boosting aims to reduce bias by sequentially training models that learn from previous models' mistakes. Stacking takes a meta-learning approach, using another model to learn how to best combine the predictions of multiple base models. Let's explore each of these in depth. Bagging, short for bootstrap aggregating, is probably the most intuitive ensemble method. Here's how it works. We create multiple bootstrap samples from our original dataset. These are random samples with replacement. We then train a separate model on each bootstrap sample. Finally, we combine their predictions by averaging for regression or majority voting for classification. The beauty of bagging is that it can turn a high-variance model into a more stable one by averaging out the individual variations. Random forest is the most popular implementation of bagging. It combines hundreds or thousands of decision trees, but with a twist. Each tree is trained on a random subset of features as well as a random subset of data. This double randomness makes the trees more diverse and reduces correlation between them. Random forest is incredibly versatile, works well out of the box, provides feature importance scores, and is relatively resistant to overfitting. Boosting takes a completely different approach. Instead of training models independently, boosting trains models sequentially, where each new model focuses on the examples that previous models got wrong. The idea is to gradually build up a strong learner by combining many weak learners that each improve upon the mistakes of their predecessors. This sequential nature makes boosting particularly effective at reducing bias and can achieve very high accuracy. XGBoost, or adaptive boosting, was one of the first successful boosting algorithms. It works by initially giving equal weight to all training examples. After training the first weak learner, it increases the weights of misclassified examples and decreases the weights of correctly classified ones. The next model focuses more on these harder examples. This process continues with each model in the sequence getting better at handling the difficult cases that previous models struggled with. Gradient boosting takes boosting to the next level by using gradient descent optimization. Instead of just reweighting examples, it fits new models to the residual errors of the previous models. XGBoost, which stands for extreme gradient boosting, is the most popular implementation. It's highly optimized, handles missing values well, and includes regularization to prevent overfitting. XGBoost has become the go-to algorithm for many machine learning competitions and real-world applications. Stacking, or stacked generalization, is the most sophisticated ensemble method. It works in two levels. Level 1 consists of diverse base models trained on the original data. Level 2 uses a meta-learner that takes the predictions from Level 1 models as inputs and learns how to best combine them. The meta-learner can be any algorithm, often a simple linear model or neural network. This approach can capture complex relationships between different models' predictions. Voting classifiers are simpler ensemble methods that combine predictions through voting. Hard voting simply takes the majority vote from all models. If 3 out of 5 models predict Class A, then Class A wins. Soft voting is more sophisticated. It averages the predicted probabilities from all models and chooses the class with the highest average probability. Soft voting often performs better because it takes into account the confidence of each model's prediction. So when should you use ensemble methods? They're particularly valuable when you have high variance models that tend to overfit, when you want to improve prediction accuracy and you have the computational resources, when you're working on critical applications where robustness is important, or when individual models show complementary strengths and weaknesses. However, ensemble methods require more computational resources and can be harder to interpret than single models. Ensemble learning offers several key advantages. First, improved accuracy. Ensembles almost always outperform individual models. Second, better generalization. They're less likely to overfit and perform more consistently on new data. Third, increased robustness. If one model fails, others can compensate. Fourth, reduced risk. You're not putting all your eggs in one basket. Finally, flexibility. You can combine different types of algorithms to leverage their respective strengths. However, ensemble methods aren't without limitations. They require significantly more computational resources for both training and prediction. They're much harder to interpret. You lose the simplicity of understanding a single model's decision process. They can be prone to overfitting if not properly regularized, especially with stacking. Model selection becomes more complex as you need to choose multiple algorithms and tune their hyperparameters. Additionally, they might be overkill for simple problems where a single model would suffice. Here are some best practices for ensemble learning. First, ensure diversity among your base models. Use different algorithms, different feature sets, or different training procedures. Second, validate properly using techniques like cross-validation to avoid overfitting. Third, consider the computational cost versus performance gain. Sometimes a single well-tuned model is more practical. Fourth, start simple with methods like random forest or voting classifiers before moving to more complex approaches like stacking. For implementation, you have several excellent options. Scikit-learn provides easy-to-use implementations of random forest, XGBoost, and voting classifiers. XGBoost and LightGBM are specialized libraries for gradient boosting with excellent performance. For deep learning ensembles, TensorFlow and PyTorch offer the flexibility you need. These libraries make it easy to experiment with different ensemble methods without implementing everything from scratch. Ensemble methods are widely used across industries. In finance, they're used for credit scoring and fraud detection, where accuracy is crucial. In healthcare, they help with diagnoses and treatment recommendation systems. E-commerce companies use them for recommendation systems and demand forecasting. In image recognition and natural language processing, Ensemble methods often provide the state-of-the-art results. Many winning solutions in machine learning competitions rely heavily on Ensemble techniques. Let's summarize the key takeaways. Ensemble Learning combines multiple models to create more accurate and robust predictions. The three main approaches are bagging for reducing variance, boosting for reducing bias, and stacking for meta-learning. Popular algorithms include random forest, XGBoost, and voting classifiers. While Ensemble methods typically improve performance, they come with increased computational cost and complexity. The key to success is ensuring diversity among your base models and proper validation. So, what's next for you? Start by experimenting with random forest on your current projects. It's beginner-friendly and often provides immediate improvements. Try XGBoost for structured data problems where you need high accuracy. Practice with different Ensemble methods on public datasets to understand their strengths and weaknesses. Most importantly, always compare Ensemble performance against single models to ensure the added complexity is worth it. That's a wrap on our comprehensive guide to Ensemble Learning. I hope you now understand how to leverage the power of multiple models to improve your machine learning projects. If you found this video helpful, please give it a thumbs up and subscribe to the channel for more machine learning content. In the comments below, let me know which Ensemble method you're most excited to try. And don't forget to check out our related videos on random forest and XGBoost for deeper dives into specific algorithms. Thanks for watching, and I'll see you in the next video.